Good day and welcome back to the third part of our discussion on curve sketching. As mentioned at the end of the previous video, we will explore two additional examples in this video, the first of which is going through all 8 steps or guidelines for curve sketching. So to begin, for this function of interest, f of x equals x times the square root of x plus 1, if you have not done so already, pause the video and work through as many of these steps as you can. Once you have done so, then come back and go through this overview with me a bit more quickly. So for this function, I'm going to just go through the individual steps. This function's domain is wherever that quantity under the square root is positive. So we need that x plus 1 to be bigger than or equal to 0, which means our domain is going to be x bigger than or equal to minus 1. To find the intercepts, we start with the y-intercept. It will be of the form 0, comma f of 0. And when you substitute in 0 to the function f, you get out 0. So we have a single y-intercept, which also happens to be an x-intercept, but the question remains, do we have any additional x-intercepts? So we set our function equal to 0, and this will be equal to 0 when x is equal to 0, or the square root of x plus 1 is 0. We already knew the first root. Similarly, x plus 1 equals 0 tells us that x is equal to minus 1. So we have two x-intercepts, 0, 0, which we knew about, and minus 1, 0. In terms of symmetry, we substitute in minus x, and we see if we can somehow relate this back to f of x. So in our case, we would have minus x square root of minus x plus 1. And it turns out that no matter how hard you try, you're not going to be able to write this quantity as minus f of x or f of x. So in this case, we would just simply say there is no symmetry, which is fine. There will not always be symmetry present. With horizontal asymptotes, we need to think about what happens as x approaches plus or minus infinity. Based upon the domain, we only need to think about the limit as we approach positive infinity, which in this case is infinity, so there is no horizontal asymptote. Similarly, a vertical asymptote typically occurs when the function is undefined because you are dividing by 0. So there is also no vertical asymptote. So unlike the previous problem, from just this more algebraic exploration, we don't have a ton to go by. We know the domain, the x-intercepts, and the y-intercepts. So the properties that we get from calculus, i.e. intervals of increase-decrease, maximum minimums, concavity, will be extremely helpful. So f of x is equal to x times the square root of x plus 1. And I'll say it again, if you haven't paused the video and differentiate it, you certainly should do so. So we would differentiate this using the product rule. We would take the derivative of the first times the second plus the first times the derivative of the second. And even though it's unnecessary, I'm going to put the times 1 afterwards just to indicate that I've thought about using the chain rule. And then to simplify this as nicely as possible, we're going to get a common denominator. So I'm going to multiply the first term by the square root of x plus 1 times 2 over that number. And when we expand everything out, we have a common denominator of 2 square roots x plus 1. And in the top, you will have 2 times the quantity x plus 1 plus x. So I will write that as 2 plus 3x. And what we would like to know is when we make our number line for f prime, thinking specifically in terms of our domain, minus 1 and to the right, where is this quantity positive, where is this quantity negative, so more importantly to get started, where is it equal to 0? And note this is equal to 0 precisely when 2 plus 3x is 0, or x equals minus 2/3. So we need to check kind of points on either side of minus 2/3 and see specifically, will f prime be negative or positive? Note the bottom is always positive. 2 plus 3x in the top, if we think about this for a moment, it's a line that crosses the x-axis at minus 2/3. And when you plug in 0, it's positive. So to the left of minus 2/3, it must be negative. And you can always check a value. You could substitute in, say, minus 3/4, but if we can get that observation intuitively, as long as we do so correctly, that is okay. And that gives us immediately the intervals of increase and decrease. We're increasing from minus 2/3 to infinity, and we're decreasing from minus 1 to minus 2/3. And at that critical point of minus 2/3, we are going from decreasing to increasing. So there is a local minimum at minus 2/3. And note, we want a point to work with in a moment when we sketch our graph. So I need to know what is the function input. So I'm substituting this into the function f. And when you substitute it into the function f, you'll have minus 2/3 multiplied by the square root of minus 2/3 plus 1. So I'm going to leave that simply as minus 2/3 square root of 1/3. And now things are looking much better in terms of sketching the graph of this function, but with concavity we could probably do an even better job. So let's go ahead and find the second derivative as well. And I'm going to create just a smidge bit of room. We have f prime from above is 2 plus 3x over 2 square roots of x plus 1. And I'm going to differentiate this once again using the quotient rule. So we think inwards, low d high minus high d low. And when we differentiate this low function, we have the constant 2 multiplied by the derivative of the square root of x plus 1. So 1 over 2 square roots x plus 1. And once again, I'm going to write it, that 1 which comes from the chain rule. And this is all divided by the bottom squared. So it looks like a mess at first, and, well, it kind of is a mess at first, but note at least the 2's cancel. And let's go ahead and just try to simplify and combine a few things. So the bottom is going to have that denominator 4x plus 1. But note in the top, the second term is 2 plus 3x over the square root of x plus 1. And the first term is what? 6 square roots of x plus 1. So I'm once again going to try to write this as a single fraction. So we'll multiply the first term in the top by the square root of x plus 1 over the square root of x plus 1. And if earlier this semester you were kind of just itching to do a bunch of simplifications, we're past that point where it's okay and even necessary to simplify. So now we'll have a single fraction in the top with common denominator square root x plus 1. And the top of that fraction is going to be what? 6 times x plus 1 minus 2 minus 3x. Be very careful with minus signs and distributing through. So I'm going to write that out just to make sure I don't make a mistake. So 6 times x plus 1 minus the quantity 2 plus 3x. And then lastly, the simplification I'm going to make is this square root of x plus 1, you can bring that down to the bottom. So we will have x plus 1 to the first power times x plus 1 to the square root. So our new denominator will be 4x plus 1 to the 3/2. And in the top, we'll be left with a 3x plus 4. Whew! So we finally have a very reasonable formula for the second derivative. And if there's any confusion on that second to last step, then we just note down here to the side, a over b divided by c is a over bc, which is what we've used. What we want to think about is, where is this quantity equal to 0? So we're not quite done yet. This would happen when 3x plus 4 is 0, or x is minus 4/3. So we have f double prime. It would be equal to 0 at minus 4/3, but we're only interested in the domain of the function. And minus 4/3, note, is outside the domain. Also, we could potentially have to worry about where the bottom is equal to 0, but note x plus 1 equals 0 precisely when x is equal to minus 1. So the only interval we're interested in is the domain of the function. And if we pick the easiest possible input, like say 0, you can easily compute or just observe that f double prime of 0 is positive. And our only interval of concavity would be concave upward from minus 1 to infinity. So as I mentioned in the previous problem, there's a lot going on, but the more you practice, the more efficient this will become. So let's put this all together and graph the function. So I'm going to go ahead and just get the information down that we saw on the previous page. And note, I typically would do this just one step at a time. So in this case, we've seen that we have an x-intercept corresponding to minus 1, 0, and 0, 0. We also saw that we have a local minimum value that occurs at minus 2/3. And there's also an associated function output, and I'm not going to label that point too precisely, but you certainly could if you wanted to. That output is something a little bit bigger than minus 1. And then we can think in terms of intervals of increase and decrease. And what we saw is, because we have a local minimum at minus 2/3, we're going to be decreasing till we hit minus 2/3, and then increasing after. So that's minus 2/3. And we also saw that we were concave upward on the entire domain. So let's just play connect the dots. We start off at minus 1, 0. We decrease down to our local minimum. And then we increase upward, and we are concave up. And this should give us a rough sketch or idea of what the graph of this function will look like. So note, as we've indicated previously, these problems really do have kind of multiple parts. It's first gathering the information, and then that final step of compiling it together in terms of a graph. So let's practice this graphing portion. I walked through it on the previous example. What I would like you to do is pause the video, give yourself, a solid 3 to 5 minutes, and sketch the graph of a function that satisfies the following properties. Hopefully at this point you've paused the video and you've thought about this for a moment. I'm going to pause my video and just add a few details in here. So the problem statement tells us 3 critical points, 0, 2, and 4, and then everything we need to know about intervals of increase, decrease, and concavity. And it's worth noting there's not a single graph that satisfies these properties. We could all sketch different and separate examples that do. The reason being is we haven't given any function values whatsoever that will nail down this function. So I'm going to go ahead and, just for fun, I'm going to assume that f of 0 is equal to 4. And note, from the information we have, we increase to 0 and we decrease after. So that is going to be a local maximum. So we are starting way to the left, we're increasing, and we are concave down until we hit that first critical point. Then we have another critical point at 2, and I'm going to just, once again, randomly pick a point just for fun. And we are decreasing and we're concave down until we get to 1. Note our concavity changes at 1 and it changes again at 3. So I'm going to put those faint dashed lines in there purely to help myself. So concave down, decreasing, and now when I hit that dashed line, I've continued to decrease, but I've changed from being concave down to concave up. We have another critical point that occurs at 4, and if we're going from increasing to decreasing, that is going to be a local maximum. So I'm going to just once again kind of randomly pick where that point is going to be. We are increasing after 2, and we are concave up until we hit this dashed line. And now I'm going to try to change my concavity, and I'm going to change to concave down, and we increase until we hit this local maximum. Then we decrease, and we are concave down. So this is one example of a function that will satisfy the properties given above. Note, you could have sketched something that looks, somewhat different than this, but you very easily should be able to pick out these 2 local maximums, a local minimum, and roughly get in there where you have that change in concavity. So take some time, practice multiple examples. If you have questions, do not hesitate to reach out. So stay tuned and take care.